Okay, so I'm the lecturer and the organizer for this module. This is a horrible room to have a lecture in, I must say, but we're stuck with this for the remainder of the semester. And we won't be able to change it, so we'll have to live with it, I'm afraid. I will be lecturing you for most of the module, but at some point, Dan Smith, who is the other lecturer in the unit, will come along. Can the people at the back hear me? Yeah. Good. So that document there is on Blackboard, and it tells you what is going to happen in the module. So there will be lectures every week. Unfortunately, we are not going to have a reading week. And I will be in charge of the first 9 lectures, and then Dan will come to the 10th and 11th lecture. Week 12 is free, because if you wish at the time, we will have a revision lecture. And that depends on whether you want to have it or not. I will only have it if enough people request it. So if you want it, we will have a revision lecture. The labs will not start this week. They will start on week 3. I don't know if that's how your timetable is set up, because it might be that they have booked labs for week 2. If they are, you can disregard labs in week 2. They will only start from week 3. Okay, so even if you see them in your timetable, you don't have to attend them. We will start in week 3. The seminars, which will run every week and you've been allocated groups to, will start in week 2. So there is no seminars today or tomorrow, but there will be seminars next week. Are we all clear on that? Also, there will be 2 pieces of coursework. The first one will be a design exercise, which will be set by Dan. I think, by memory, that is set on week 4, and probably due around week 7. And I haven't looked at the course schedule for this year. The second piece of work, which is a practical exercise implementing a database, will be set around week 8 and will be due on week 12. The way which we will mark, the first one will be marked as a normal exercise and you will get it back. The second one will be a demonstration, and the marks will all be allocated in the demonstration, so you will have to come to demonstrate your system. It will be individual work, so you will not be working with other people, and you should not be working with other people unless you want to be penalized, obviously. And you will come to demonstration, and then we will allocate marks there and then for you. Okay? And then there is also an exam. This unit is, I think, is 40% coursework, 60% exam. But I might be wrong. I am right. See? It's clever of me. I'm a very clever person. So this is how things are going to work. It means that, of course, putting effort in your coursework is always worthwhile, because exams are harder. Generally, students don't do very well in exams, because generally speaking, students don't revise for exams. And that means that when they come, they don't really know what they're talking about, and they tend to perform worse. So if you do well in your coursework, which is very feasible for this subject, you go to your exam with a wood mark, and that means that you're going to be possibly okay in the module. Obviously, if you fail, you have to reassess. That is not a good idea for you, and it's not a good idea for me. So I would like everybody to get a good mark. Unfortunately, that is not always achievable. And some people always fail. So we'll try to make sure that it's not you. So do you have any questions on the organization? No? All happy? Okay. So now if you have been doing what you should be doing, you should have your lecture notes, because I've put them in Blackboard ahead of the session. The idea with all of this is that I am not going to print out any materials for you, nor will the seminar leaders, nor will the lab leaders. You are supposed to turn up to the sessions with the relevant material printed. So I will try to put them ahead of the day. I will normally send you an email when they are ready for you to print. And then before you come to the lecture, make sure that you have done that. Equally, before you go to the seminar, make sure that you have done that for the lab. So, and My name, by the way, is Beatriz de la Iglesia. Might be hard for you to pronounce. It's a Spanish name. I'm Spanish, but I've lived in Norfolk for a long time, so I'm half Norfolk, half Spanish. Even though my accent is more Spanish than Norfolk. I'm been here for 22 years, so I qualify as being a little bit Norfolk. My email you will know because you can access it, and there is all that kind of detail. So if you have questions, you can also always email me. So before I start, let me tell you something about the way I view things. Now, I consider attendance absolutely essential to everything. And I mean really essential. And I am going to come down like a ton of bricks of anybody who will start to miss lectures, seminars, or labs. There will be attendance taken at every event. And if you miss out for more than 1 week, I will take action. Okay? So I expect to see you here every single time for everything that happens. Only things that I will qualify will be if you're ill, in which case you should contact me or your seminar leader or your lab leader to say, look, I couldn't make it because I was ill, and give some reasonable excuse. And when I mean reasonable, I mean reasonable. Waking up at 11 o'clock is not reasonable if the lab is at 9 o'clock, which might be your case. Now, for those that attend, there is a reasonable chance they will pass the module, okay? If you don't attend, it's quite hard to pass the module because you get disconnected, you don't know what is going on, you begin to lose sight of the topic, and it goes from bad to worse. So attendance to me is the number one thing that you have to do if you want to pass. And I think hopefully all of you here want to pass the module, because otherwise there's not much point in being here. But attending alone isn't going to make you pass. In fact, nothing that I do is going to make you pass, because I can't teach you anything. You have to learn. Teaching is a very hard act. Learning is what happens. So I can enable your learning, but I cannot teach you anything. So you have to make your own effort to learn this. What I can do is I can make it interesting, I can give you the right starting point, but a lot of it is going to have to be you putting in your own work, reading the book, reading the notes, going to the seminars, preparing for them, etc. Okay? So this is what I really expect of you. So not only do I expect you to attend, but I also expect you to participate. And by that I mean if you're in a seminar, you should be trying to answer the questions and not playing with your iPhone or whatever is what entertains your mind more. If you go to a lab, you're supposed to be engaging with the live material and not looking at Facebook, and so on. Okay? And then if you want to be a really top student, and some of you will have your aims on a first class degree or a 2+ degree or whatever, what I really think you need to do for that is to do a little bit of extra preparation. And that means that you really need to read ahead, read afterwards, not just read the lecture notes, but try to take a little bit of care of other things that are there for you so that you expand your knowledge. And those are the things that people that really want to excel in a subject should do, not just for my subject, but for any subject, okay? So those are the rules of engagement for this. And as long as you know, I tend to get, funnily enough, nearly 100% attendance, which is good, isn't it? But this is because I make such a point of it. So try to fall in with my regime, and then we will all be happy. So that is me. And I know at this point I've scared the life out of you because I look quite scary. I am quite approachable, even if I initially come across as being scary. And I am quite willing to help people, especially those people that help themselves. I'm less willing to help people that don't turn up for anything and then come and ask for help because they're lost. If you try, then I'm willing to help you. If you give up on yourself, then there is going to be less time available. So having said that, which are the preliminaries, we're now going to go into the first lecture. And the first lecture that we're going to do is really an introduction to databases. And also before I start, let me tell you that this is an introductory course to database systems. So I'm not going to go to introduce any very advanced material. Some of you might have come across databases before. I might have come across some of the stuff that we're going to do. The idea is that really, I want to make sure that when you leave, you really truly understand the concepts in databases, database manipulation, etc. So we're going to keep it fairly simple. If you can excel at that, that is great, and you will get a very good mark. I'm not going to be too challenging. Well, I hope I won't, but even for some people that will be challenging because it's not a subject that everybody understands. So we'll try to introduce the concepts from the beginning. Some of you might know some of this already, but we're still going to go through it because I have to give you a good overall introduction to database systems. So today we're going to look at things historically. So we're going to look at what was there before we had database systems, because that's important in order to understand why database systems have become so popular and why they are kind of driving a lot of the world at the moment. So what we're going to do through this lecture is to define and discuss database systems and also file-based systems, which was what was there before. And we're also going to look at the advantages and disadvantages. Halfway through, we will have a break before we go into the next part of the lecture, which is going to discuss the database environment. Now, for every one of these lectures that we do, I will give you some reading. When I mention reading in the Connolly and Beck book, that is more or less compulsory. You should be reading that. When I ask questions in the exam, I could extend to anything that I ask you to read from the book. I might not cover absolutely everything in the lecture. I will cover most of the important concepts. But you should read the chapters and get a feel for what is said. There is also going to be quite often other additional reading that will not be examinable material. So I won't put questions on the exam on the additional reading, but I have papers in a folder there that you can read, like the original papers on the databases by code, etc., which, if you are interested in the subject, you might care to look at. That is voluntary. But the reading of the book is not. You should really be doing that. You don't have to buy the latest edition. I'm happy with a slightly older edition if you find it cheaper. You can go to the library and try to borrow the editions there. So don't by any means spend too much money on books, because I know students are hard up and they don't have a lot of money. If you can find a slightly cheaper, slightly older edition, most of the concepts that we cover will probably still be covered in the 4th edition, although now we're up to the 5th edition. Okay? Any questions on that so far? No? Good? So, Connolly and Beck chapter 1 is what you should read. The other things are, one of them is a paper that is in the reading folder of Blackboard, are, if you want to learn more, if you're interested, you can read them, but you don't have to, they won't be examinable material. So, the first thing that we have to start thinking about is why do we want to study databases? Why is it an important topic for people like you doing degrees in computing science or information business or business information systems or whatever? And the reason is that when you look at the world today, the majority of the data in the world is stored in a database. Structured data is what is stored in the database, and that is everywhere around the world. The idea of structured data is that it has a regular format. So what we are talking about is generally data where we can see columns or attributes or fields that contain information, and then for each of those we might have records that belong to individual objects which give us particular information on those attributes. So it has a regular format. Generally, this is a table with columns or attributes and records. It always has with it a machine-readable content, description of the content. So not only do we have data, but we also have what we call metadata, and that is data that explains the data. So we have additional information on that data. It is increasingly common. So if we think about a university like this, there is a database. It's not the best database in the world by any means, if you have to use it like us. But it has things like a student record. So I can look up my advisees, I can look at what they're registered for, I can look at their marks, etc. If you are a student, you can access your marks. You might not be able to access the marks of other students. You might access certain things about your record. There is also going to be other forms of other databases, not only the student database. We have the library, for example, which will also have a database, which will contain students, and it will have things about the books that are, or the journal articles, etc., who is borrowed them, from what length, etc. So there's more than one collection of data. We also have the Unit or module catalog, so we're also going to store information about the different modules, like to BOA, who is the lecturer, what kind of a structure do they have, how many pieces of coursework, etc. So that is also going to be part of it. And things like staff records, my record, how much do I earn, what position I'm in, how long have I been have I held my position, etc. So all information as well. Now, when I said that, if I now ask you today to think of a database you might have interacted with since you woke up today, can you think of any database you might have interacted with in your day-to-day? Not the student database, but any other. Can anybody think of any?
Contacts on your mobile phone.
Yes, indeed. If you contact your mobile phone, you are accessing a database because that is going to have store your number, the numbers you access, what kind of contract you're on, what are your minutes, etc., etc.
Emails?
Emails. If you use your email, again, it's probably going to be a database somewhere. That, in this case, might be part of the student record, but not necessarily because you might have an outside account, and the company that hosts you should have to know your email address, details of your account, etc., etc. Anything else?
Facebook.
Facebook. Again, that is a database because you have to have a user account. Indeed, they have a lot of information about you because we hear this with the concerns of privacy. They know all the posts that you've done, the pictures that you've been tagged on, what games you play, etc., etc. So they store all sorts of information on all sorts of users. What else you might have interacted with today? Anybody had to pay a bill? Like an electricity bill, or a gas bill, or a telephone bill? Any company that bills you is going to have a database of customers. If it's the electricity bill, they will know your account, the kind of meter you have, the usage you've had over the years, the tariff you're on, etc., etc. If you book the flight, again you're interacting with the database, which holds the flights, the flight information, the reservations, the hours, the airline, etc., etc. So we can see that every day from the moment we wake up to the time we go to bed, we're interacting with databases, and they are very important to us. But they're not the only way of storing information. This is how we store the structured information. There is a wealth of other information which is not structured. Can anybody think of examples of unstructured information that a company, let's say UEA, may have? What do I mean by unstructured? Not in a table format. So any kind of text you might think of will be unstructured information. So for example, I have a lot of emails, which might not be structured, but the content of those emails might be relevant to me, I might have to search them, etc. I might write Word documents, documents for particular course descriptions, documents, letters, etc. All of those are also data that is not structured, but necessary for the running of the business. I might have spreadsheets which contain information on costings or whatever. So not all of the data in the world is structured, but the structured data is what we interact with the most in terms of companies. And let me remind you that the lectures start at 10 minutes past.
Yeah, sorry.
Okay, so try to be on time, otherwise we get all not happy. So what do we need to study then? If we can see that databases are important because they're all around us, and to interact with any business we need to understand the databases, what do we need to study about them? There are two things that really matter to us. One of them is the structure and the other one is the content. So those are the things that we really need to get to grips with. From the point of view of accessing the data, we need to learn how to manipulate it. And this is what we're going to do as part of this course. We're going to learn about a language which is called a data manipulation language, SQL, which is a standard data manipulation language. And that is going to be an important part of our course, because an important part of the data, of course, is interacting with that data. So we might do interaction with the data using SQL, and that might be what we call ad hoc interaction. We type a query, the system returns the data that we want. We can also interact with the database by an applications program like Java and the JDBC interface. So we're also going to learn how to do that. We are also going to learn how to write programs in a language such as Java which interact with the database, request data from the database, bring it back, and do any formatting, displaying, or handling of that data. So part of what we're going to learn is the database manipulation. We're also going to learn a little bit, not a lot, about database management systems. And this is the piece of software that handles the database. So the software that handles the database is a quite complex software, as we see. It has to have a lot of functionality. It has to provide concurrent access to the database, safety, etc. And we need to begin to understand how that software works and the complexity of it. So that is part of what we will study in this course as well. So to begin to do that, we have to take a historical view of what happened to databases and how they were developed. And if you were as old as I am, without speculating about my age, when I started studying computing science, which I did at this university, we used to have these little Apple Macs, because they were also fashionable at the time. Then they went out of fashion and they came back. But they didn't even have a hard drive. We used to have floppy disks that we had to change, and so on. You know, so things were quite far, and I'm not that old, from how they are now. So technology has moved rather fast. So if we think back over the 1960s, when the development of databases began, there were people doing things that required, the computers were started to be used at that point. I remember the first computer I saw, I might have been about 13 or so. My father had one in his office and it was huge. And probably didn't do much more than calculations and printing pictures with little X's. But at the time it was quite amazing to see that, because I've never seen a computer before of any kind. So when they started to have, in the 1960s, one of the main projects that actually started the development of databases was trying to land a man on the moon. That was generating a lot of data. It was quite a big scientific project. They were using computers, and they were beginning to generate more data than they could handle successfully. So then that kind of got them thinking into what was the best way to handle data in the context of using computers, etc., effectively and efficiently. So that is how things started. And they started with a company called IBM, which is still around today, and a system called the Information Management System, or IMS. And initially, what they had was an arrangement of records for the data that was a hierarchical arrangement. So in order to navigate the data, you needed to understand this hierarchy. You needed to understand where was a parent node, where was a child node, and how you went from one to the other. So at that point, trying to access data meant that the structure of the data was embedded within the application, and you needed to understand that structure in order to navigate the data. For the time, because they were handling, by our standards, probably not that much data, that might have been okay, but they soon realized that this probably wasn't the best way of handling large amounts of data. There were at the same time another system called the Integrated Data Store, or IDS, which was developed by somebody called Bachman, who became quite famous in the area of databases. And that was parallel, another kind of project that was making the scientists question how you should handle the data effectively. And as part of that second project, they started to come up with these bodies that will then set up the standards. So they set up this group called the CODASIL DB-GT group, which came up with some proposals for how databases should be managed, how data should be handled, etc. So there was the beginning of this kind of like trying to standardize databases and data management and data manipulation. Now, both the IBM and the GE system led to having to understand the structure of the data, because the second one, instead of having a hierarchical structure of records, it had like a network structure of records. So there was less restrictions in the way in which the records were placed, but still, you needed to understand that network in order to navigate the data. So that let only programmers being able to access the data and program access to the data. And that was problematic as you needed more and more access to the data. So both of these approaches led to complex structures that require detailed programming. So we had the programmer as the navigator. The programmer had to be the one that navigated the data each time. And that was very limiting from the point of view of what you could do with the data. So things moved on slightly, and in the 1970s, a very clever person who became very well known in the database area, called Code, started to think differently and thought, what we could do is use the things that we know about maths, because maths are, is an area where we have definite understanding of how things work, and we can have languages that can manipulate the data. So let's think of how to define data and manipulate data from a mathematical perspective. So he came up with a new kind of model, which is a relational model, and that has been the model that has survived to today. So it was a very good development, because up until now, nobody has come up with a better model for accessing large or storing and accessing large amounts of data. The idea is that you had then simpler structures, and that you had query languages that were accessible to end users. So you didn't need to have programmers navigating the data. And associated with that were a number of result systems. One was called the system R, which was developed by IBM. There were other systems being developed again at the same time to test the concepts of the relational model. And they all led to commercial systems in the 1980s, where companies such as Oracle, DB2, etc., brought their software. IBM brought DB2, Oracle brought their database, and it became like a commercial thing instead of a research project. So then you start to see commercial systems for database, relational database commercial systems. And then in the 1990s, there was a lot of object orientation in programming, and the concepts of object orientation became very important. So there were some developments in this area of object orientation, because they could support more complex applications where the data might be more complex, like geographical information systems might have quite complex data, CAD might have quite complex data. So they started to develop then new models of data around object orientation. But that hasn't quite catch on, and the system of choice is still the relational database model. So most of the times that you go out there, the systems you're going to encounter will be relational database management systems. They might have extensions that allow you to have object orientation within them, but mostly the systems that continue to be in use are relational database management systems. Are we so far all happy with that? Are you all following me? Am I talking too fast for you? You are all happy. Good. Isn't it fabulous to have a happy class of so many people? So we have to understand how things were before we had databases. And before we had databases, what we had was the file-based approach. And this was very much something that was conceived because every program will manage its own data. Every applications program will define and manage its own data, which at the beginning of computing seemed to be a good approach. So if you have to write an application to do something, you define your own data structures, you define your own access methods, etc. So for example, if I have a sales department there and a controls department there within a particular company, each of them are going to have their own files that they are going to access for their own data. Each of them are going to define their own file handling routines. Each of them are going to have the file definitions. Each of them are going to have the data entry points for how people keyboard the data in, and their own reports for how they report the data out to the user. So this is kind of like a method in which applications are isolated and they're handling their own data. And that was the initial approach to data management. It was called the file-based management system. And what we have with that is that if, for example, there we have a sales file, and we have a property for rent and an owner and a renter file within them, each of them are going to define a number of attributes of the data. So for a property for rent, which is an object that we want to model, we might have things like the property number, the street, the area, the city, the postcode, etc. From an owner, we might have an owner number, a first name, a last name, address, telephone number, etc. Now, as we move to the contracts file, what we find is that some of the data is stored in both systems, so there is repetition of the data. And duplication of the data is problematic, because when we have duplication, it is harder to control the quality of the data. So we're finding that because each part of the company is managing its own data, they are having to redefine some of the things. So for example, if we go to a lease, we have things like property for number, etc., which might also be in the property for rent. So what we're finding is repetition of the data, duplication of the data, because different systems are implementing data bases or data management, file management, isolated file management system. So what we have to do, what we used to do in this file-based approach is, it is following the manual file-based system idea. So if you have a house, if you in your house are half organized, you might have your own files to, let's say, file your bank statements and your electricity bills and however. So you will have some ordering of your files within each of the areas, etc. That is counting that you have some organization in your life, which might not be the case with the students. Maybe you just have a big pile, you stick it all in. But as you get older, maybe you will get to this idea of the file organization. The idea is that you put things that are similar together, so I might put my bank statements together, my electricity bills together, etc. And then you arrange them in a given order. So my bank statements, I might arrange them in time order, from the older statements to the newer statements, etc. This is going to be okay if I want to do simple processing, like I want to insert, update, or delete an individual record or a big set of records. But when I start to try to do more complex processing of the data, this system is not particularly efficient. I also have one problem, is that only one user can access one file at a time. While that user is accessing the file, nobody else can access it. So if you imagine if things run like that now, if there was a flight and somebody was trying to book it, nobody else will have access to that flight until that person finishes the booking. That's not going to be very good, because we all want to be able to do things at the same time in the global world that we live in. And also, if you want some reporting out of your data, suddenly you think, actually what I want to see is I want to view my overall spend in the last year. Any ad hoc reporting that isn't programmed is going to be very difficult to achieve, because you do not have ad hoc access to the data. The access to the data has to be programmed, the reports have to be programmed, so there are limitations in the access that you can have of the data. And if you want further reports, then you need to employ programmers, and the programmers are expensive, so you're going to find that there is a bottleneck in there. So if I had, for example, 10,000 student records in name order, and they were registered in different schools, then I want to say arrange them into school degree, or program, or degree program name, etc. It becomes quite hard if the data is sitting in separate schools and I have to look at all the students, put them together, then try to organize them. It's not very efficient processing. It's not very efficient if I have to find all the students who have a first-class degree. Again, they are like, each school is maintaining their own data, so I have to go to different systems, access the systems, pull out the students to meet the criteria, so it's not particularly efficient. If I then want to cross-reference the students with the library loans, then it becomes even more efficient, because again, I have to go to another system, look at the alternative students, so it's not going to be leading to very good or efficient data access. So what we want to do, so in this scenario what we have is that each application program is managing its own data, and is managing the access to the data, and is writing the programs that access the data. So we have a number of problems. One of them is the isolation of data. The data in this department is not visible to the data in this department, so we have isolated data that doesn't kind of like, is not easy to put together. We have duplication of data. So if, let's say that you have a record in the library which was independent of the record in the school. If you don't change your address in the school, but you don't change it in the library, suddenly there are two addresses for one student, and we won't know which one is the right one. So duplication of data is complex because it leads to poor quality of data or problems with the quality of data, which we do not want to have. We're also going to have duplication of the programming effort. If the library wants to do something, they have to do their own programming for that to access the data that they have. if my department wants to do something, again, they have to have a programmer to develop that. So a lot of people are doing perhaps the same thing over and over again. So that is not going to be particularly efficient either. And we have a big issue which we will explore more in the next lecture, and is that this issue of data dependence, which is very important to the database system. If the definition of the data is within the application program, then we have this data dependence, because we need to understand the structure of the data in order to access it. And what we want is to have data independence. We want to be able to change the data without affecting all of the applications that use that data. So I want to be able, for example, let's say that my address field for a student is 200 characters, but then I come across some students from other countries which have much larger addresses, and I have to increase the size of my address field. If I have data independence, I do that, and I don't necessarily affect all of the programs that access the student data. But if I don't have this data independence in the old system, every time you change something, you affected every application programming that was accessing the data. And that means that then you have to reprogram everything, leading to a large effort, and leading to further inefficiencies. So that is why quite an important issue. There is also an issue of incompatible data formats. Every kind of language, different systems will use different languages. One system might use COBOL, another system might use C, another system might have used BASIC. Each of them are going to define the data in a different way. They have their own formatting. So when you're trying to cross-reference data from one system to another, you have to deal with these formatting issues. You have to account for the fact that in something like COBOL, there might be a fixed format spaces data like that, where every bit of data has its own kind of like length allowed. If we go to a C string format, it might be that it's the space that delimits the data, but there is no fixed length allocated to each of the fields. If I go to BASIC, then it might be comma separated. So as I work with data from one type of application to another, I got to be constantly converting formattings or dealing with the difference in formatting. So that is again going to be problematic from the point of view of accessing the data. So that is what we have with the file-based approach, which is the old approach before we had databases. The problem that we have is that the definition of the data is embedded in the application program rather than being stored separately. And that dependence is a bad thing for data access, because it means we might have to change every application program every time we redefine something in the data. And we want to move away from that. So that is one of the drivers for the development of better ways of storing data. And also, we have no control over the access and manipulation of data, beyond that which is imposed by the application program. So the application programs are managing all the access, and we really don't have control over that either. So those are two problems that we have to overcome. We have to come to a solution where, since we are having more and more data, and this is thinking back to the 1960s, 1970s, computers are becoming more powerful, not obviously by our standards, but by their standards. They are getting more data, so they need to have more efficient access to the data. So they started thinking, the scientists, about better ways of doing it. And what they come up with was this idea of database processing. So the idea is that now we are going to drive all of this from the point of view of the data. So before we were driving everything from the point of view of the applications. The applications were driving the data management. Now we're going to have a rethink, and we're going to allow the data to drive all of the process of data management. So it's a different way of thinking. It's what we call a paradigm shift. And we will come back to that in a minute. So now what I want is I want to have a central repository of data, which is going to be managed by a piece of software. This is going to be my database, and the software is going to be my database management system. And in having this repository, I am going to give from that one place access to the data to all the different departments. So instead of having to store the same data over and over again, I only store it once. So I cut down on the redundancy of the data. And if I don't have data redundancy, it becomes easier to maintain the consistency in the data as well. So I now have a DBMS, and I have a data entry and reports for the sales, and a data entry and reports for the contracts, but they are all driven by the same database management system, by the same access to one database. So now, as I look at what I have now stored in that, property for rent, owner, renter, and lease, and if I compare it with the previous approach, I will realize that I have cut a lot of the duplication. Now I'm only storing each thing once, in one particular place. So I don't have to worry now if my address changes, I don't have to change it in several places. I'm only going to store each thing once, therefore I can change it in one place, and I'm done with that. So each entity is only stored once, and by entity I mean either a property for rent, an owner, a renter, or a lease. And the idea there is that I have the entity name before the bracket and the set of attributes that define that entity within the brackets. Are we all happy with that still? Anybody has any questions? No? As scary as it might be to ask the question in a big room, I will get you to occasionally interact with me. And as we develop an understanding of each other, this will become easier and easier. You will see. So what we have is what we call the database approach. And when we talk about the database, what we're talking about is a shared collection of logically related data and a description of the data. Because remember that in the database approach, we have the data and the metadata, the data that describes the data. And this is going to be designed to meet the needs of an organization, no longer the needs of an individual department, but I am thinking about the data in a global sense. So I look at my enterprise and I think, what data do I need to store for this whole enterprise? And I might design my whole database for the entire enterprise, not for one part of the enterprise. So we have a shared collection of interrelated data. Within that, I am going to define things like entities, attributes, and the relationships between those objects that are defined as entities. Entities are going to be like objects. So a student is an object in the student database, so that will become an entity. A coursework might be an object, so it will become another entity perhaps, depending on what attributes I have to store. Attributes are going to be the facts that I can store about an entity. So if I have a student, from the point of view of a university, what matters to me in defining a student? It might be the name, the address, the telephone number, what modules he's enrolled on, what marks he has got, what did he do before, how well did he do before. All of the things that define my object will become attributes. And once I have defined entities and attributes, each individual real-world object, i.e. any of you students, then becomes a record in the database. So that is an individual occurrence of an entity with a set name and a student number, etc., then becomes a record or an instance. And remember that we have said we are going to store a description of the data, the metadata, because that is going to allow us more efficient access. And it's also going to allow us this process of making the data independent. Storing the definition of the data as well as the data means that then we can change that definition without necessarily affecting all of the programs that access that data. So we are going to have that metadata, which is going to be stored in something called the system catalog. And the other important thing about this is that we have moved to the context of the entire organization. So our data is no longer thought for a particular part of the organization. It has to meet the entire organization's needs. So what we have is, to run that, we need a piece of software called a database management system. And that is going to be the software that sits between the database and the application for the users. All of the access to the database is going to be managed by the database management system. There will be no access that goes to the database without going through the database management system. So the software there handles all of the access to the data. There is this paradigm shift that I've mentioned. If we think about data in terms of databases, we're moving from thinking about data in terms of the application that it serves to making data the central part of this. So we start designing from the point of view of the data, and then we think about the applications later. Before we were thinking about the applications and designing the data around the applications. Now we're thinking about the data, and once we have defined the data, then we think about the application. So there is a paradigm shift in the way that we think about things. And there is a number of users that are going to be accessing a database. We have people like the database administrator who takes care of the database and controls things like who can access what, the efficiency, the performance, etc., etc. We have end users who are going to be writing queries and are going to access the system in an ad hoc manner, or perhaps through reports that we provide or screens. We're also going to have database designers who are going to be making sure that the design of the database is correct. With anything in life, a poor design leads to a really rubbish thing. I don't know if you've ever come across poor design, but I certainly have. I, for example, had a kettle in my house where the lid was on top, so every time you try to open the lid, you burn your hand with the steam. The thing in the handle was on top of where the steam comes. So that is a bad design. It was very pretty, very expensive, and it looked great. Stainless steel, but actually the design was poor, because whenever you try to open the lid, you burn your hand because the handle was on top. So that was a poor design. So design is important in everything in life. And of course it is important in databases. If you have a poorly designed database, you're going to annoy the users, and probably they'll end up making mistakes. So database design becomes very important as well. Now, the different users might overlap in the real world. So the database designer for a small company might also be a database administrator. If the company is large, the roles might be very well defined. So they might or might not be the same. So what do we have in a database? First of all, we have languages. Now, the languages that we care about and we are going to study are a data definition language and a data manipulation language. The data definition language is the one that we use to define the objects, so we can define the entities, the attributes, the length of the attribute, the type. We can build the metadata with that. And then we have also a data manipulation language, which allows us to delete, insert, update the data. In our case, we do that both things through SQL. SQL has a data manipulation language and a data definition language, so we'll be studying them both. And then we also need some subsystems as part of the DBMS, and they have to provide alternative views of the data. Now, if we have a single database, all of the users don't want to see all of the data. As a student, you want to have access to your marks, but you might not be interested in the staff salary or the staff's responsibilities. So because you have a shared data resource, you need to be able to provide each user with the view of the data they need, and no more. So our database management system need to be able to provide us alternative views of the data that fit the usage that we need. They also have to provide us with security. This is very important to us. We don't want other people accessing our data and deleting it or doing something with it. So we have to be able to say who can access what part of data and for what purposes, for insert, for update, for delete, etc. We also want to have integrity. It's very important that the database management system maintains the data, which is a global, very important resource with the highest possible integrity. So we don't want the data to be corrupted in any way. So the system has to maintain that. We want to also be able to produce a concurrent system where many users can access the system at the same time without ill effects for anybody. So I want to be able to book my flight knowing that if I book the last seat, nobody else is going to turn up and have booked the same seat as I did. That is what we call managing concurrent access. And in the event of any failure, the system has to be able to recover to a consistent state. So if there is a problem with the electricity supply, or if there is a fire, or if there is corruption of the hard disk, the system has to be, the database management system has to ensure that we roll back to a state of consistency. So there has to be recovery things. And there has to be also access to the system catalog, which we have said is an important part of the database. So what kind of things do we gain from having a database approach? Well, first of all, we can, as we said, we're going to eliminate duplication. So the first thing that we're going to gain is we're going to have control of redundancy. If there is data that is redundant, it will be under the control of the database management system. So redundancy will only be allowed when the database management system is controlling that redundancy. We're also going to have more consistent data because the changes, once we don't have redundancy, if I change my address, I only have to make it in one place, and that will be visible to the library, to the school, and to every other body that accesses the data. We can also enforce any company standards that we have, because the data is a global resource, so it's easier to enforce standards. We can have this data independence, where we separate the definition of the data from the access to the data. So that means that we can then change the data without affecting all of the users of that data. It might affect some, but not all of the users of the data. We have better sharing of data, because more people can access the same database. It's not isolated like before. And we can have better reuse and interrelating of data. So all of those things are good things in the database management system. We also have better security, because we can control who accesses what and for what purposes. We can have better integrity, in the sense of having business rules that are applied to the whole database, etc. Validation of the data at the entry point, etc. We have better concurrency, because we allow many users to access the same shared resource at the same time without interface. The system has to control that. Recovery, so we have backups, we have logs, etc. So if we have a system failure, we can always recover to a consistent state. You wouldn't like the database tomorrow to fail on the university and all your grades so far have gone. Maybe you would like it if you have really bad grades, not so much if you have really good grades up until now. You want to make sure that whatever information is held about you is there, no matter whether there is a fire or whatever. So the database has to access that. And we're also going to have greater programmer productivity, in the sense that programmers are free now, because they don't have to be doing all of this access continuously. We are giving the end user a way to access the data. So we have better programmer productivity. The users have better access, and we can also optimize complex navigation. So all of those things are good things that we get. Is everything good about having a database? So is a database the solution that fits all problems? Not necessarily. A database management system is a very large and very complex and expensive piece of software. So you don't want to kind of build a massive bridge to cross a little river. Not always the right approach. So you have to think that there is the code complexity of the DBMS. So if you're handling a small amounts of data and your accesses are relatively simple, a database might not be the right approach. You might still be better managing the data within your program, depending on what access you're going to do. If there is a failure, because now we have a shared resource, it will impact upon everybody. So you have to beware that the failure impact will be higher, because we have a shared resource now. So if it goes down for one person, it goes down for the entire organization. You have to spend more on hardware. You have to spend more on software, because all of these things, generally you need a powerful server to run the database. Then you have to invest in a commercial, sometimes, database management system, so that will add to the cost. If you were using something else, you have to convert all the previous workers. You've got to train them, so that has a cost and implications, etc. And if you have very simple navigation, it might be poorer in this complex system, because there are many checks that have to be done. So if you were only thinking of simple data access, it might not be great. So before we have a break, you can now tell me if you're having, what was the second thing? Attendance, participation. So if you have been participating. Is it true or false? A database management system is a collection of application programs that perform services for the end users, such as the production of reports. each program defines and manages its own data. So is that true of a database management system? Those that think that this is true, raise your hands. Nobody thinks that. Those that think that is false. Okay. And some of them are decided. Okay, the false ones were paying attention because it is false. The undecided may have been asleep. They should try to wake up for the second part of the lecture. So we go on and ask, which of these are disadvantages of the network and hierarchical approaches? And the network and hierarchical approaches were the earlier approaches that we talked about, where we have the records either in a hierarchical or a network approach. So which of these have disadvantages? Complex programs have to be written to answer even simple queries. There is minimal data independence. There is no widely accepted theoretical foundation, or all of the above. Those that think that A is the right answer, raise your hands. You're all looking at each other to think, does anybody dare to raise your hands, right? Let me see what others are doing. Okay, B. Those that think that B is true, there's at least one. What about C? There is no widely accepted theoretical foundation. And what about D? All of the above. Yes, the majority of you got it right, because it's all of the above. So all of those things are true of the earlier systems. And then, one more, who is responsible for maintaining database consistency? Is it the database application, the end user, the database designers, the database management system, the DBMS vendor, or all of the above? So if I think about the data consistent, is it A, the database applications, who thinks that is A? I should get one of these. You know, we have these gadgets that allow you to vote and you see, but it's too much effort. I'm just going for the old-fashioned raise your hand. B, end users, who thinks it's B? C, database designers, at least one. D, database management systems, a few of them. The DBMS vendor, and all of the above. Well, I think you are kind of like right in both ways. I think the most responsibility falls with the database management system because it has to handle a lot of issues of consistency. But in fact, all of the above to some extent, because as a user you also have to have certain responsibility to not enter incorrect data, etc. So all of them have some responsibility, although mostly it will be the database management system. And then the last one is, which of the following is not an advantage of using a database? Lower cost, flexibility, up-to-date information, controlled redundancy, multiple user interfaces, or access control. Which of these is not an advantage of using a database, or a database management system? Is it A? Who thinks it's A, lower cost? Yeah. Anybody for B? Or C? Or D? Now you all think it's not, because everybody put their hand in A. Or E? Or F? Okay, it is A. Yeah, it's the lower cost that is the major problem in the database management system. Okay, we're going to have a break for 5 minutes, and you can think about that yourselves. And then we will regain